seems to work. Okay, hello everyone. I'm always a little bit nervous if this part of the tutorial is too much highlighted in the previous sessions. But I will do my best to introduce quantum game theory, at least the way how I understand it. I will share my screen. I hope you all see it. And
yes, we can see.
Okay, perfect. So what I will try to introduce is to give you some overview of the quantum game theory, which is basically the idea that quantum probability theory, or the aspects that we learned this week regarding quantum cognition or quantum decision making, can play out in the strategic context. That means the topic which is usually dealt with in so-called game theory. I will give you some a review of some basic articles that introduce the idea of quantizing the games, and I will try to make some typology of those approaches in this talk. So first of all, some outline. I would like to start with introducing game theory. I don't know whether everyone is familiar with it, and its crucial so-called solution principle, which is Nash equilibrium. I'm positive that everyone heard about it, but I would like to remind us what does it mean and what does it mean in the context in quantizing the games. Then I will introduce one experimental puzzle that seems to be against the predictions of classical understanding of game theory. And then I will conclude with the ideas how we can quantize the game. So games, how to translate them into the framework that we've been introduced to in this bootcamp. First of all, what is game theory? Game theory, if you're familiar with rational choice theory, then game theory is basically this theory applied to strategic context. And that means to the situations where the players, so-called players, deal with the decision-making problem, but not on their own, but they have some like counter player or opponent in this context. So basically, the outcome depends on the decision of all players involved in the situation. Why we care about game theory? It is because we study games. There are like about 100, 120 different games, but we are not particularly interested in those games, but we understand them as a representation of broader social contexts. So you definitely know Prisoner's Dilemma, which is used to understand different dilemmas of collective action. Game of Chicken, which has been used, for example, to understand nuclear deterrence, Battle of Sexes, which is used for the coordination problem in society, and so on. So those games are just like models for broader social situation that we try to understand. And why game theory is intriguing for someone thinking about quantum social science. In my perspective, it's quite intuitive way to scale up the ideas that we have on the individual level to social level. So if we have cognitive science and a use of quantum models to try to understand cognition or decision-making of individuals, then through game theory, I think we can scale it up to the problems of multiple players or even society. So that's the promise that at least is there in this quantum game theory project. What we will see quite a lot in this presentation is this payoff matrix. Once again, you're probably quite familiar with that, but I will just specify the main aspects of it. The payoff metrics, as the name suggests, specify payoffs, so what the players get from the situation if it ends up in a specific way. And so we have two players here. This is the most simplest game where we have two players and each of them has two strategies to play. So player A, Alice, has strategy K or L, and Bob has strategies X or Y. And based on their combination of those strategies, we have specific outcome which the players get from this situation. So for example, if player A, Alice, plays strategy K and Bob will play strategy Y, then Alice will get 0 and Bob will get 3 from this decision-making problem. So you see what I said at the beginning, that game theory is basically about taking decision-making theory to this strategy context, because then you need to think about the other player to play the game well. Okay, and I will jump to the main, definitely well-known social concept, which is used in classical game theory, which is Nash equilibrium. So the basic idea that game theory asks is what we would basically expect from a rational player. And so on the slide, we have one of those models, one of those games, Battle of Sexes. The game is about, so we have a pair, you can imagine couple, they think about how to spend the evening, and they do not have means to communicate with each other. So we have a husband and a wife deciding what to do with the evening. They cannot communicate. And you see from the payoff metrics that they would really like to spend the evening together. So their payoff is 3 or 2 if they spend it together in theater or in the soccer play. But their payoff is actually 0 if they fail to coordinate and they end up in different places. And you may ask yourself, or you may ask game theorists, what is the rational strategy of a player in this situation? It seems that there are some like good outcomes in the game and some bad outcomes in the game, but if we are facing the game from the perspective of player A, and we have to decide whether to go to theater or to go to the soccer play, we may not be sure what to actually do. And the answer has been provided by John Nash, and this is famous John Nash equilibrium. Nash equilibrium is defined as a set of strategies from which no player has a unilateral incentive to switch to another strategy, knowing other players' strategies. That's the formal definition, but may sound difficult, but we may simplify it with this other notion that you see on the slides. Nash equilibrium is the strategy which is the best response to what the others are doing, or what the other player is doing if the other is only one other player. So what you can say about this game is that this game actually has 2 Nash equilibria, and we will find the Nash equilibrium with using this strategy of the best response. So for example, if I'm a player A, and I have some idea, some assumption that the other player will go to the theater, my best response to this strategy is to go to the theater as well, because if I go to see a soccer, I will get 0, but if I go to theater, I will get 3 from the situation. And similarly, if I go to the theater, the best response for the other player is to go to the theater. So it's mutually best response. What is the best response for me is the best response for the other. So we would say that theaters, the combination of strategy is one of the Nash equilibria of the game. Obviously, there is, or you can possibly see that there is another Nash equilibrium, which is soccer and soccer. So once again, if I have some assumptions that the other, or some reason to believe that the other will go to see a soccer game, I will go to soccer because it's best response to what I am expecting from the others. And the other way around, my opponent, his or her best response is to go soccer because I go to soccer. So these are basically, it's called Nash equilibrium because it's something what we would expect the game may end up, some kind of solution which does not have much forces that would force the players to go elsewhere. So it's like pulling equilibrium of the game. So in this particular game, we would say that this game has two Nash equilibria in pure strategies. It's a combination theater, and soccer. And what is important and crucial for quantum game theory or game theory in general is that it's based on the assumption of so-called shared knowledge of rationality. So basically, I as a player assume that the other player is rational, and I assume that the other player assume that I am rational, and so on. So we need this like a collective understanding of rationality, which means maximization of the utility that we can get from the game. Nash equilibrium, the concept is not limited to poor strategies, which you may once again be familiar with. There is so-called mixed strategy Nash equilibrium. So even in the classical games, we can think of players mixing the pure strategies, meaning that they will play strategy A with some probability and strategy B with another probability. What we would require that this classical mixture, which is defined by these probabilities P1, P2, and etc. Pn, which are the probabilities of playing individual strategies. We would just require that they will sum to 1, which just means that the player has to play one of the strategies with the probability, at least one, exactly one of the strategies with the probability 1. And what is the Nash equilibrium in mixed strategies? So we, for example, may say that my strategy would be to flip the coin and to go to theater if I see tails, and go to see soccer if I see heads. And Nash equilibrium in mixed strategy is basically the same as we had with pure strategies. So in the previous slides we saw those two Nash equilibria, which are the Nash equilibria in pure strategies, but there is the next another, which is the Nash equilibrium in mixed strategies. It means that if I decide to combine my strategies as the A player, to decide make a probabilistic distribution of my strategies, 60%, 3/5, to go to the theater, and 40% to go to see a soccer, then the best response of the other player is similar strategy, only a mirror of this. The probabilities of these strategies are mirror of my strategies my probability distribution, because the game is symmetric in this way. So that's if you are actually solving the game. If I teach it to the students, I say look for this Nash equilibrium in pure strategies, but do not forget to look for Nash equilibria in mixed strategies, because they may be there. And what is the result that we know? Why is it known as Nash equilibrium by John Nash? Is because of his PhD thesis, which was written in 1950 on comparative games. And in this thesis, he proved that every finite game has at least one Nash equilibrium. And that means directly that if there is no equilibrium in pure strategies, there is a Nash equilibrium in mixed strategies. So if we do not have this stable solution of the game in pure strategies, we know that we have to look for mixed strategies. And just a quick note, I said it last year, and I think it's important to mention it once again. His PhD thesis was, I believe, like 26 pages long, and he got Nobel Prize with that. So I think you can do a miracle with your PhD thesis if you are interested, if you have good idea. That's probably the story of his PhD thesis. And to give you just one example of the game that has, we use this logic of Nash equilibrium. So we look for mixed strategy equilibria, because there are no equilibria in pure strategies. Imagine a penalty kick, which you are probably familiar with. I just created this payoff metric. So we have a player here, and he can kick the ball to the left, to the center, or to the right. And a goalkeeper that can jump to the left, stay in the center, or jump to the right. and we have some payoff metrics, which, for example, specify that if the player kicked the ball here to the right, there is no chance that the goalkeeper will keep it if he jumps left. And yeah, so this, for example, out of 10 attempts that the score of the player will get 9 goals, and he will probably miss the goal post in one of them. So you can construct the payoff metrics by trying to understand the social phenomena that you try to understand. And if you make the calculation, if you look for Nash equilibria, you will find that there is only one Nash equilibrium, which is a mixed strategy, which once again is classical mixture of the 3 strategies that the player has. So for example, for the player is to kick the ball to the left with the probability 7/18, which is about 40%, to the center 4/18, which is about 20%, and to the right 7/18%. Over 18, which is about 40%. And for the goalkeeper, it's interesting that his mixed strategy in Nash equilibrium only have strategies to jump to the left and to jump to the right, and he should not stay in the center, never, because then he would give the player the advantage by staying in the center. But it depends obviously on the payoff metrics. But by the way, if you ever heard of famous, for example, goalkeepers, they basically study the players before the game, and they construct, in a sense, this payoff metrics, and this gives them basically the idea what they should do to maximize their utility from that particular penalty kick. Okay, and the last in this first part, reviewing classical game theory, I have to mention the most prominent model in social sciences, which is prisoner's dilemma. You probably know the story, so I will not go into details, but we have two people that were convicted by the police, and they can either cooperate with each other, which means remain silent and does not say something about the other convict, and their other strategy is to defect, which means to cooperate with the police and say everything and so on. What is interesting about this game is a prominent model because it seems to analyze a lot of social phenomena, including, for example, tragedy of commons, like environmental degradation in this planet. And what you can see, what you probably recall from some classes, is that even though there is an outcome that seems to be quite interesting for both players, because by mutual cooperation, they can reach a quite high utility from this game, even though they can get more if they defect but the other cooperate. The solution of the game is the Nash equilibrium of the game is actually defect and effect, and it's basically this fear that the other will defect, which force the players to also defect. So we would say this game has only one Nash equilibrium. It's quite strong because defect is actually a dominant strategy. So no matter what the other will do, you always will be better off if you defect. And so this is called dominant strategy equilibrium. And if you find dominant strategy equilibrium, is it also always Nash equilibrium of the game? And I just introduced this game to revise that we know it probably, and because we will need it for the second part of the talk. I don't see any. I see something in Q&A, but it's probably from the previous. So from the previous. So unless there are any questions, I will go to the second part. So everything clear so far? You're probably familiar with those aspects of classical game theory. Okay, so let's see what we can do with this. And first of all, I would like to introduce one experimental puzzle that is known with respect to Prisoner's Dilemma that seems to suggest that something is wrong with this classical understanding of games, and especially these classical social principles. So I will go through some experimental results that are puzzling from the perspective of classical game theory. So first of all, this is something what's known in political science problem of cooperation, problem in question marks, because we obviously would be keen to see it more in international relations, but at least our classical social principles say that the states, for example, when they are facing prisoner's dilemma, they should not really cooperate with each other. In IR, we use it to, for example, model arms race. So the situation where two states face an imminent conflict, and they decide whether they will build their armies or not. And what I think, what I mean by the problem of cooperation, if you we may say that people stubbornly refuse to stop cooperating, and if we use the concept of Nash equilibrium, we would assume that the cooperation in such situation would be 0%. So yeah, definitely there will be some people who do not fully grasp the game from the perspective of rational theory, but Nash equilibrium say that there is actually dominant strategy. The game should really have tendency to end up in mutual defection, and therefore the prediction for the classical game is zero cooperation. But if you do the experiments, and this has been repeated many times in numerous experiments, you would see that classically the observation is between 20 and 40%. That means that between 20 and 40% of the respondents in these situations or players will cooperate, even though Nash equilibrium suggests that they should do something else. There is a vessel explanation. If you are from IR field, you probably know the article by Axelrod from 1981, in which he actually reported the results of the tournament that has been of the tournament. He invited basically computer algorithms to play Prisoner's Dilemma against each other, and yeah, this tournament has a clear winner, which was tit for tat, which was strategy tit for tat. This strategy says that the player should cooperate in the first round and see what what the opponent will do in the game. And if he meets cooperative strategy, the strategy continues to cooperate, but whenever he or she is defected, and in the next round he will defect back. So it's like this idea for basically revenge for what happened in the previous round of the game. Why is it not contradicting those two things that I have on the slides? Because there is a big change what they did in the experiment, and what I described when I was explaining that Prisoner's Dilemma actually has one Nash equilibrium, is that they introduced repeated games. So the computer algorithms play the game repeatedly. I don't recall the number of rounds, but it was high, like 100 or more. And you may probably see that if you have a strategy that is only defecting, it will not collect much of the points because it will only get one from each of the rounds. But if you actually have strategies that find a way to understand that they are able to cooperate, that they will maybe collect in each round 3 times as much points. So it was the reason why this tit for tat strategy was able to win the tournament, because it was willing to cooperate unless meeting a defective strategy, in which case it defected back and haven't let the defective strategies to get more points. And so why is this not in contradiction? Yes, Michael?
Yeah, I have a question regarding once a once they defect, would they be trapped in the defecting pattern, or is there a chance in this experiment that they just spontaneously start cooperating again?
That's a good question. In the original tournament in 80s, I believe, it was only tit for tat strategy, but it says that you will repeat what the other actor have done in the previous round. That means that if the other will start cooperating, then you will go back to cooperating, and you will cooperate for the rest. Yeah, so you will only revenge in the next round, and in the round after that you will again repeat what just happened. Yeah, so there's a possibility to go back to cooperation, definitely. But the problem with the strategy is actually that it can end up in this vicious cycle of mutual revenge, that if I cooperate and the other defect, I will defect back. And if the other strategy is willing to cooperate, then we will basically repeat punishing each other. So that's one of the problems with the strategy. And actually in the later works, they come up with a strategy where you basically take the first defection as an error. So you are more patient with your revenge. And so if you are defected twice, you will defect back. So that's more room for errors, for example.
Okay, thanks.
Yeah, but yeah, it's possible to go back, but not if your opponent will say, okay, you defected me, so I will defect you for the rest of my game. But if there's a will to cooperate, they will go back. But what is the problem? Why is this not a contradiction? Because while the tit for tat makes sense in repeated games, and I should say in infinitely repeated games. So, for example, if you are talking about meeting your neighbor every other day, then you have incentives to cooperate because you will meet him the other day, and it's nice to have a positive response from him. But in the one shot, this logic does not exist. Yeah. So if I meet, and this was the case of many experiments, when they said, okay, you will play this game only once with your opponent, and then you will meet another opponent. So it's not possible to create this trust in the game. So it's still a contradiction, even though we have this repeated game or tit for tat strategy in repeated games. Yeah. And it's one of the major results in international relations or in classical game theory. And when I was talking about this experimental puzzle, I would like to introduce, I was talking about this study from Shafir and Tversky from 1992, when they actually have a really clever experiment. They played Prisoner's Dilemma with the participants, but they divided them into 3 groups, and they provided them with different treatments. The first one, in the first treatment, is they said to them that the opponent has defected them. So they passed them the information that the opponent defected. And in this case, 3% of them has been willing to cooperate back. So they were like altruistic, even though I'm defected, I will cooperate. In the second treatment, second group, they said that an opponent cooperated. So imagine that in this decision scenario, it's no longer a game because you have clear strategy of the other player and you decide only to cooperate back or to defect. In this scenario, 16% of the participants were able to or willing to cooperate. And in the last treatment, it was the clever move in the study. They provided them no information about the opponent, so they played usual Prisoner's Dilemma. And in this scenario, 37% of the participants have been able to cooperate. So you see that in this study, it actually meet my information from the previous slide that the percentage of the people willing to cooperate in PD is between 20 and 40%. And I don't know whether you see the problem, but there is a clear problem with classical probability theory in this result. And this is something what's called Savage's sure think principle, which says that if I'm trying to calculate or evaluate what is the probability that player A will cooperate in the game, it should be equal to the probability that the player expect the other to cooperate and cooperating back, so conditional probability, what I will do after seeing cooperation of the other, and plus the probability that the other will defect multiplied by conditional probability, my willingness to cooperate after seeing the defection. So this is the formula that has to be correct for Kolmogorov probability theory, classical set theory. And what you can see, we have this conditional probability here. So willingness to cooperate after seeing cooperation. It's this first value from the first treatment. This willingness to cooperate after seeing defection is the second number from the second treatment. And we don't know what is the probability that the other will defect. We don't know that, but we know that it's 1 minus probability that he will cooperate. There are only two possibilities, and this classical either or logic, the other either cooperate or defect. So it has to be 1 minus probability that he or she will cooperate. You probably see that the total probability according to Kolmogorov theory should stay between those two numbers. So it depends how much cooperation we expect from the other player, but the overall willingness to cooperate should stand within the bounds of these two numbers from the two treatments. And this is clearly not the result from the experiment. So it seems that the result contradicts the classical constraint, and it's called disjunction effect, and it's something what Joyce and Emmanuel and others has talked in their lectures at the bootcamp. But I just introduced it here because it's directly in game theory context. So we see that something is happening there. And I would say that after a week of the bootcamp, we can say what is wrong there. And if I would say, yeah, we can use many words for that, but for example, this contextuality would be a good way how to see it, because clearly this is the willingness to cooperate in one context. This is the willingness to cooperate in second context, and this is the probability to cooperate in once again another context, and therefore we cannot just sum them together and to expect that they will be equal, because we are changing the context between the treatments. Okay, so but that's the experimental puzzle. Why do players cooperate more often when they do not know the opponent's strategy? And this is, I would say, one of the openings problems that open doors for quantum game theory. And this is just like some mapping of the space where we can look for the answer. And I think there are at least three assumptions of the classical game theory that are quite challenged by ideas of quantum social science or quantum social cognition or decision making. The first of them is the assumption that actions are limited to prescribed strategies. So in the classical game theory, you have strategy A or strategy B, and you can have their classical mix. So you can flip the coin and choose one, or A or B. But it's always either or. The result is one or the other strategies. And one of the ideas that you may ask, if you are somewhat familiar with quantum probability theory, what if the strategic space is broader than just these limited to those prescribed strategies? Second assumption, which is challenged, I would say, by these results, that perspectives are compatible. So We may ask whether players actually consider their strategies and their expectations about the opponent in parallel, whether they are cognitively able to do so, whether they are willing to do so, are they able to measure both at the same time. So basically the question is compatibility of observables. What if my strategy and my expectation, thinking about myself and thinking about the opponent in the game, are non-compatible? We cannot think about them in parallel or at the same time. And the last one, which is probably the most challenging, the assumption that players are separate entities or their actions are independent. So usually we assume that those players only have this mutual knowledge of rationality, but there is nothing what connects them. So they act independently, they do not communicate, they do not have information about the others. But we can ask what if their actions or they actually are not independent. So they are somehow entangled. We may use this concept. Okay, so these are only some ideas that suggest that quantum game theory may have some answers to this challenge of this study. Okay, and now I will go to the second half of the presentation, which introduce some ideas how we can actually quantize the games. So if we, by quantizing the game, I mean, what if we relax some of the assumptions of the classical game and introduce this more like richer structure of quantum probability rate, what we can see what happens in the games. And I would start with the idea introduced in the paper in '99 about introducing quantum strategies. So it's a paper written by David Mayer, published in Physical Review Letters in year '99. And if you are familiar with Star Trek, you probably know Captain Picard and Q, which Q is this supernatural being that is, I would say, posing many troubles for the Starship Enterprise. But the story goes like this of this game. So you have Starship Enterprise, which is facing some calamity, and Q appears on the bridge and offers to help, provided Captain Picard can beat him at penny flipping. And penny flipping is the game which goes like this. So Picard is to place a penny head up in the box, whereupon they will take turns, Q, then Picard, then Q, flipping the penny or not. They can decide what to do without being able to see it. So they probably somehow shake the box or whatever, and they will either flip it or not. Q wins if the penny is head up when they open the box, yeah, and Picard wins if the other side is up when they open the box. So we can classically, how we would understand the game, we would construct this pair of metrics. So you have Picard here, he has only one round in the game. So Q has 2 and Picard only 1. So Picard can either not flip or flip, and Q can non-flip and non-flip, non-flip or flip, and flip, flip and non-flip, or flip or flip. And based on this, their mutual, or yeah, the combination of their actions, you will see the payoff from the game. So it's either -1 for Picard if neither will flip the coin, sorry, and it's 1 for the Picard if he flips, but Q decides not to flip it, and so on. So it's fairly, yeah, they do not have the same number of moves, but the game is fairly symmetric, or I would say fair classically. You cannot really get an advantage if you are starting the game or if you are the second in the game. But what, yeah, so how now we try to start quantizing the game. Yeah. So the suggestion that Mayer came up with in '99 article is that you start to think about the vector space in which you can represent the game. And as there are 2 outcomes of the games, up or tails up, you have natural orthogonal basis, which would be consisted of those two vectors. As we know, initially the game is head up. That means that that it's aligned with the basis vector h, which represent the observable head up. So we have the starting vector, we have Hilbert space, we have vector space, 2D vector space, and we may think how the classical strategies would look like in this space. You can use, we need these operations, these matrices that represent the strategies in the game. So do not flip means that you apply identity matrix to the vector. So if you multiply this matrix with the vector, you will get the same vector. Not surprising, we are not flipping the game. And if we decide to flip the coin, then we may use this matrix, which just like if there is a 1 up, it will go down, and if 1 is down, it will go up. So it will just flip the coin as we want. And because we are not restraining Captain Picard in any sense in this classical understanding of the game, we allow Picard to play mixed action, which so we can construct another operator, another matrix, which would be a linear combination of flipping or not flipping the coin. And the result is a classical mix. So you will have with probability P the game coin flipped, and with probability 1 minus P the coin remaining heads up. Yes, Michael?
But this classical mix, I wonder, this should not be taken literally, this plus sign here, because it would lead to a quantum superposition in a sense. Not be a mixture state anymore.
Yeah, it's a classical mixture. Yeah, so we in whatever Picard, so it's not literally, you're right.
Okay, so the plus is a different character here than adding these two things together. It's just combination, like an and sign also.
Actually, in the paper, he used different notation because he introduced density matrices, but because I don't want to, because we did not introduce it in the tutorial, then I was just like simplifying it for the purpose of the presentation. But you are right. It should be basically either. Either tail up with the probability P or head up with the probability 1 minus P.
Yes, and there's a question by Heather in the chat.
Okay, sorry.
Can you see it?
Yeah, I can see it, but I would probably address it later on if we can, because I think we should first review, if it's okay for Heather.
Oh yeah, don't derail it. It popped up right now. Take it. Please.
I think like the other applications would be more relevant to what you are asking. Yeah, so okay. I would like to review the rest first, and then we can address it definitely. Yeah. Okay. So so we basically have these classical strategies or classical mixture. Yeah. So Picard can, in theory, flip another coin and decide what to do with the coin in the box. And as you may guess from the payoff metrics, there is no deterministic solution, no Nash equilibrium in pure strategies. So if you always flip, then the other, if he understands that you will flip, he can get advantage in the game. So there is only one Nash equilibrium in the game, which is to mix the strategies with the probability P 1/2 for Picard. So basically, not letting Q know what will be the result. only in this case it will be pure chance if you are playing classical opponent, but not Q in this game. Okay, so nothing surprising probably here. And how we change the game with thinking about quantum strategies. So what Mayer introduced in the game, in the paper, he introduced like broader class of strategies. He named them quantum strategies. And the idea was that he can represent them with a unitary matrix. So with the matrix of this form, where we have two complex numbers, and A and B, and we have the minus A complex conjugate and B and B complex conjugate. There is this classical restriction that we need, for the matrix to be unitary and for to be able to somehow manipulate the quantum state. And after manipulation, the state is still of unitary length, so representing the quantum state one again. Okay, so and by the way, this matrix is you can have A1, in which case you would have non-flip, B equal to 1, in which case you would have flip. So this includes the classical strategies, but as I said, the strategic space is broader, more options for Q, because Q is able to manipulate quantum world somehow, and so we can think of number of various strategies. So, for example, polymetrics would qualify as this strategy, and this if applied to the original state, initial state, you would just have this state 0 and I without being able to say what does it do with the coin actually. But it's not what used in the paper. What Mayer suggested for Q is another example of this broader class of strategies, which is the Hadamard gate that was introduced yesterday in 2 talks and by Michael. So this gate or this strategy, quantum strategy, looks like this, and basically what this does to the initial state. So we have Hadamard gate applied to the initial state, and after this we will have superposition of heads of coin, heads up and heads down. Yes, Michael?
Yeah, just a question regarding your definition of U here.
Mm-hmm.
Where is the non-move, like just the identity included? I can't see it because then A should be 1, but then
You are right.
There's some.
I will have to review this.
Yeah.
This is from the paper, yeah. So I just take it from.
Could it possibly be that it's taking all of these old ones and only adding the new ones that are quantum? So you have the original also, maybe?
Yeah, that's possible. I thought that the original strategies are included, but I was not like careful enough to see it. So I would have to review it once again. But what Matt is suggesting is definitely an option. But it doesn't. I mean, it doesn't change the argument of the paper. The argument is that you include another strategy or class of strategies, and the question is whether the originals are part of this class or not. Okay, thanks for the question. I will make a note and I will look at it. But what happens with the Hadamard gate? So if you apply this, so we will have this superposition, superposed state, and if you try to visualize it, maybe it's not perfect, but you can imagine that the classical strategies flip the coin or let it be as it is, but the Hadamard gate actually place it on the edge. So in fact, in this like visualization, there is potentiality of both options, classical options in there. And what is interesting, so we let Q play this new quantum strategy, and so he creates this superposed state, and then there is a move of Picard. Picard can either flip it or keep it, not flip it. But as you see from the calculation, it's quite simple, but the result is the same. So no matter what Picard do, the outcome is the same. And then Q applies the Hadamard gate once again. And if you apply it, you will get the results that Q wants, because heads up means Q is winning the game. So, and just to clarify one point here, we said that we let Picard to use this classical mixture, but you know, he may create probability distribution and play one or the other with certain probability, but the outcome, yeah, he will use either or. So he will either use F or non-F. So no matter what is the probability distribution, the outcome will be the same, and the Q is able to collapse it the way, or not collapse it, but to change it back to the original state, which is what he wants to win the game. And yeah, if you imagine what just happened visually, and once again, it's TwoDimensional model, it does not say exactly what is happening in the matrices, but you have the coin head up, you place it on the edge, then Picard do something with this, but maybe rotate it somehow, but it's still on the edge, and then Q can lay it down to the original state without problems. Okay, and the idea that Meyer introduced in this paper is that, or his conclusion is that well-crafted quantum strategies can beat classical moves. But obviously it's, you know, well-designed quantum strategy used for a specific game without much generalization in this paper. Okay, so, and yeah, and by the way, we discussed it last year with Michael, that it's very difficult to actually understand it with connection to like a real quantum system, physical quantum system, because you basically let Q manipulate the superposed state. So that's but I cannot really say what would be the classical, not classical, but physical analogy of this game actually. But Q is this supernatural villain that can do anything, so it's probably fine for the paper. Okay, and I will just check the questions, and if not, I will go to the idea that I presented at the conference in Vexia in June, but I believe it allows us to summarize what other approaches exist in quantizing the games. So there is, I would like to present some general scheme that we may use when we are thinking about what are the options here. And hopefully the presentation will still work. Yeah. So I will use Prisoner's Dilemma as the example here, but it does not really matter what games we will be talking about, but to have something in mind, we can think of Prisoner's Dilemma. And basically, I think the general idea of quantizing the game is to think of the initial state as the linear combination of observables. So something what we were covering in this tutorial quite a lot. So basically the idea is that we need some vector space, and in this vector space there are some the observables will be specified by certain vectors which are orthogonal to each other, and these orthogonal vectors represent the observables that are mutually exclusive. So for example, yeah, and that's interesting questions. What does it mean in the games? So the question is what observables we should represent with those orthogonal basis vectors. And there are actually two options here. One is thinking of those observables as strategies, and one is thinking about those observables as outcomes. So once again, the strategies are cooperate or defect for the player A, or cooperate or defect for the player B, and the outcomes are for, so for example, mutual cooperation, mutual defection, defection of player A and cooperation of player B, or defection of player B and cooperation of player A. And if we introduce this idea, then you can think of the initial if you think of the observables as strategies, so we can observe what is the strategy of player A and what is the strategy of the player B. We may write the initial vector as the linear combination of, in this particular basis, so strategies of the player A, or either in the as the linear combination of vectors that represent the strategies of player B. But the other option, maybe I'm not going too fast, but we will go through the more examples later. So the other option is that we think that there are, or we work with the fact that there are 4 observables, and those observables are the 4 outcomes, which so this is something what we have seen in this tutorial. We would basically create not 2-dimensional space, but 4-dimensional space, where the basis of this space would be one of the possible bases, but quite important one would be tensor product of so combination of the strategies instead of the strategies. So then we will have these 4 possible outcomes as basis vectors of our space: mutual cooperation, cooperation of one and defection of the other, defection of the other, or cooperation, sorry, defection of the first and the cooperation of the B player, and mutual defection. And these alpha, beta, gamma, delta has to meet this normalization criterion that we use in defining quantum states. Okay, so the general idea is that we can construct the game or represent the game in either 2-dimensional or 4-dimensional model. And actually both of them has been used in the literature. This is why I like what is new here, what I presented at the conference is this like general framework, but there are papers that represent the game in 2-dimensional, and there are papers that represent the game in 4-dimensional model. Okay, so in 2-dimensional model, what is the meaning of thinking of game theory in 2 dimensions? So as I said, initial state in this model is linear combination of mutually exclusive, meaning orthogonal vectors representing the strategies. So either this or this in strategies of myself or in strategies of the opponent. And if we think if we connect it to what Joyce, Emmanuel, and many others said in this bootcamp, you may think of basically this representation in 2 different bases would lead you to think about sequential decision making, because if you for example ask what is the probability that the actor will cooperate, you will project it into this basis. But if you ask what is the probability that the opponent will cooperate, you will project the initial vector into another basis. So we would think about sequential decision making, and we would say that the first person and the third person perspective in the game, so thinking about myself and thinking about the other, are considered in sequence, which leads to the possibility, if those perspectives are incompatible, to possible interference or order effects. If we think about 4D model, then I already said that, but initial state is linear combination of the outcomes, not the strategies, but combination of strategies. and that would mean that we would think of the simultaneous decision making, meaning that we assume that the actor is able to consider both perspectives at once. And it's not necessarily the sequence, but he or she considered both of the strategies together. And it leads quite naturally to the possibility of entanglement of those strategies or the players. And I will show you what we mean by that. Okay, so that's the general idea. And yeah, sorry, I have an example here. So for example, as we said, entanglement is, so we would recognize the state as being entangled if we cannot factorize it into the factors that would belong to player A and player B. And for example, some states are entangled, some states are maximally entangled, and good examples of maximally entangled states are those two Bell states, so-called Bell states. For example, in the first one, from this full formula that allow for all of the combination, you have only mutual cooperation or mutual defection, and they have same weight, so they are equally probably. But you will see that if the game is actually described, or if we can represent the actors with this state, then there is actually no dilemma in Prisoner's Dilemma, because they either will end up mutually cooperating or mutually defecting. So the forces that leads to the actors, individual actors, to defection are not really there, because 3 and 3 is better than 1 and 1 for both players. So I would say quite intuitively, we see that if we have maximally entangled states which have this particular form, then we would see maximally correlated strategies, either mutual cooperation or mutual defection. And as I said, the dilemma is not really there. Okay, I will not go into the question, but we can discuss it later if we have time. Okay, and then I give you some examples how this works in, I hope, remaining 10 minutes, and I would like to devote 10 minutes for questions. So how we can apply this general scheme to quantizing the game. And I will first start with two-dimensional model, which can introduce this idea of non-compatible perspectives. So Prisoner's Dilemma, it's actually results from my paper when which was the research I did during my PhD, when I played the Prisoner's Dilemma game with about 1,000 participants online, at first at the Ohio State University and later on online. And so the idea, as I said, is that there are two perspectives in the game. First perspective is what I do, and the second is what I expect from the other. And if we think them as non-compatible, we can see whether the changing order of those questions has no effect, whether there is no order effect in this setting. And so in my experiment, I used two different treatments. I first asked half of the participants what is their strategy, and what is their expectation, and second half, what is their expectation, and then what is their strategy. So interchanging the order of the perspectives. And I will not go into describing the model, but because you heard about it several times during the bootcamp, it's quite similar to, for example, this Bush and Gore question, where we imagine that the different order of the questions first leads to so if I have this initial state here, if I first ask, what is your strategy, then you first project the initial vector into the vector subspace stretched by the cooperation vector, then you normalize it, and then you, if I ask what is your expectation, you will project it to the either cooperation of the other or defection of the other. But if I ask you in the opposite order, then you first have to project it into the third perspective, third person basis, and then normalized and then project it back to the to my own perspective. So we may, yeah, that's the expectation of the model. If perspectives are incompatible, then we would see an order effect. But if we use this beautiful result of Joyce and Jerome Buzeware and others, we would see that the QQ equality still applies. So I will just quickly review the results of this experiment. So first of all, we expect the order effect. That means that the probability that the actors will choose cooperation and as his strategy and then expect cooperation from the other is not the same as the probability that the player will expect cooperation from the other and then choose a cooperation as his strategy and so on. So the order changed the probabilities of those probability distribution. I will just show you the results. So here you have each combination of own strategy and expectation about the others, and blue columns are starting with self perspective and black columns are starting with other perspective. You see that you probably see that there is a clear difference, and it's statistically significant. And if we look at the numbers, you just see that, for example, people are willing to cooperate and expecting cooperating much more likely than if they start from the other's perspective. So intuitive explanation from my perspective is that if people start to cooperate, then they are more willing to cooperate than if then compared to the situation when they first expect the others, and because they have worse expectation, then they follow up with their own cooperation less likely than in the previous case. Yes, Michael?
Yeah, this is really cool because this is experimental data. But I wonder whether, I mean, you will build a quantum model out of this and probably in the next slide, but there seems like, looking at the data, there's symmetry here, like kind of, you know, here in the blue bar, very left is highest, and then the black bar is at the very right is highest, and then it's like this symmetry is this captured by your quantum model, reproduced, and is this a universal evidence you observed? Yeah.
Yeah. That's a good question. The point is, if I go back to this, that in the two-dimensional model, then you know, this second projection is symmetric. And so probability from going from C to C prime is the same as probability from going to from C prime to C. And yeah, that is creating some symmetry in the project in the expectation. That's right. But what I just wanted to say, because that's probably what's so amazing about this result, is that, you know, these probabilities are different, which does not really say much about the function of your model. I mean, we created the order effect with this manipulation. But what is also, I will probably go to the next slide and we can go back to this, is that there is this other prediction of this quantum model derived by Jerome and Joyce and others, which says that even though PC prime is not equal to PC prime C, you still should see that PC prime plus PD prime is equal to PC prime C plus PD prime D. So mutual cooperation and mutual defection, there are some in the first person perspective should be same as the sum of those two in the other person perspective, which is actually what you can see quite well in the data. So yeah, Yeah, so what it means that this blue one plus this blue one has to be equivalent to this black one plus this black one. So this symmetry is there thanks to the QQ equation. And yeah, I don't know whether I addressed the question properly, but
yeah, kind of. Yeah.
Yeah, and regarding, you know, in this paper we work only with probabilities, but in current work we extend it. I do not have it in the slides, but the idea is basically that you have, because, you know, from the making prediction for the game theory, you basically means that you start only from the payoff matrix. So this is what define your game. And our idea is that with this quantization, we translate the utilities from individual cells to probabilities to individual actions, and then we will build a two-dimensional model from those probabilities with more degrees of freedom. So we need two variables there, and that yeah, one of the ideas that we currently work on with Katarina Moreira, that we have observational data of some games, and that we will fit those two parameters to those data, but it's only two parameters. So yeah, you know, the degrees of freedoms of the model is much lower than the number of the observations. So we should be able to see whether the model fits it well or not. But I do not have it here, unfortunately.
And then another question, a comment,
Yeah.
because you mentioned, and since it's ongoing research, it would be interesting whether in such a setting you can address this question by choice, like who argues or says that a certain percentage of the people are more classical, a certain more quantum. I wonder what you see.
Yeah, I partially have answer to it, but I because it goes to my typology between 2D and 4D models. Yeah, because 2D means that they construct, at least in my idea, cognitive space which is non-compatible, where those two perspectives are not compatible, and 4D means that you create a space where they live together well. And actually, one of the findings that are presented in the paper, we checked for, you know, we look for several groups of the players, whether there is the difference in what they play, how they play it. And the only factor that we find to be significant was gender of the players. So it seems that women play the game differently than men. So that's partial answer to this question you asked to Joyce.
Very interesting. Cool. Thanks.
Yeah. So, but yeah, I think it has not been picked up by others, and that is more to be done in this direction. So that's yeah, great like avenue for research. Okay, so and I will finish the four-dimensional model, which is quite interesting, I would say. So how to quantize the game with the idea of introducing the four-dimensional representation of the game. So I will turn back to Battle of Sexes, because it was the game which was used in one of the pioneering paper by Marinato and Weber in 2000. All of these papers are from either 1999 or 2000 or 2001, which is interesting because it means that there were not much follow-up on those papers. And what they, yeah, so if you think of this game, so it's a coordination problem. We somehow would like to end up in the same place, but we do not have means to communicate. So it's, yeah, this is this famous problem. So if you are lost in Paris, you and your mate, you are lost in Paris, then, and you cannot communicate, where would you go to actually meet back? And yeah, so it's basically this kind of problem. And so we have four-dimensional strategic space, which the basis is the combination of strategies of individual players. We allow, as I said, this in this four-dimensional model, the players to build this vector space which allow for the combinations. If we assume that the initial vector was a product of the two, that means that the quantum states is factorizable. So we can, I should use the indexes here probably, but so we can divide it into the factor that goes to the A player and the factor of the B player. Nothing interesting is going on. We would get to the classical model. But if we say that the initial state is not factorizable, for example, this Bell state, then you see that you basically, in this example, that means that, for example, if you have this initial state, then basically the player won the game because they can only end up in the place together, and there is not a possibility that they will be in different places. What is interesting with this result, this is what they basically show in the paper, that if we entangle the players and that means that the initial state is not factorizable, then we may change the character of the game, including, for example, Prism dilemma no longer being a dilemma and so on. What is interesting is some insight into this game. So I would say the dilemma still exists. So if I'm player A, I have still two options to go to the theater or to the opera. So they are both options are existing in the state. If A is equal to D, it's actually equally likely that I will pick T or O, but so I do not know whether T or O, they are equally likely, but the pair will always end up at the same place. So this, I think, really grasp the idea of entanglement. So we have full uncertainty about individual strategies, but we have full certainty given this particular vector that they will meet there, because there are only two options. They don't know which one will be chosen, but they will end up in the same place. But the interesting question is whether this is still the same game. So whether we have this correspondence principle, whether this limitation of the quantum states to particular entangled states, what does it actually do to the game? And I will end up my talk with probably the most famous paper written by Eisert, Wilkins, and Levenstein in 1999. What they did, they also tried to deal with Prism's dilemma, but they introduced more general scheme, which introduced to play with the concept of entanglement more than just simply like introducing one of the possible options. So what we have here is basically quantum circuit, and so basically you have two so initial states, which so the actors starts in cooperation, but then you have some entangling device which somehow entangle those two, and you enter the game with this psi 0, which is those C's after this entanglement, and then you apply unitary metrics. Each player apply unitary metrics on this general state, and then you have inverse and adjoint. What's the dagger is inverse self-adjoint, if I'm not mistaken, Michael. Hopefully I'm correct. And then you have the final states, and which you will measure. And so what they, so I already described it. So I will just show you what they did in the paper. So you have the initial states. So we have the tensor product of a cooperation of the two. You apply J to this, and it has a specific form. It's an exponential of minus I gamma tensor product of 2D matrices divided by 2, and the matrix is like this, which change the cooperation to defection, if I'm not mistaken. And yes, so you would have to think how does it look like, but you can write the psi 0 vector as cosine of gamma half multiplied by CC, tensor product of representing mutual cooperation, plus I and sine of the same angle of mutual affection. And what is interesting is that gamma here actually represent like measure of entanglement. So if you have a 0, then the game is fully separable. So the original state will be only C, because cosinus of 0 would be 1. So we would have this part of the initial state, and cosine of 0 is 0. So we will have not the second one. So then no entanglement of those two. But if gamma is pi divided by 4, it means that we have maximal entangled game. So we have 1 over square root of 2 here and 1 over square root of 2 here, plus multiplied by I. So we have a combination like this Bell state, fully entangled state. And obviously gamma, it's not like 2-level system. You can have whatever gamma, and basically where you have the value that you set for gamma will define how much entangled is the state. And so you apply U, so some manipulation of the product, and then you disentangle it and measure it. So what is interesting is that they once again introduced this general strategy U, which they wrote in this form. So it's matrix of 2 parameters and unitary matrix. And maybe I got the idea from here about flipping and unflipping the game. So the strategy, if you want to keep cooperating, then you will apply this U, where you take theta as 0 and phi as 0, and you will get the identity matrix. We will not change the vector that you manipulate. And if you want to switch the affection, then you would take pi for gamma and 0 for for theta and for phi, and you will get the manipulation that would allow you to switch to the affection. So basically this would correspond to the classical strategies, but they introduce in this paper this Q move, which is given by those 2 factors, and the Q matrix look like this. So we have Y and minus I and minus I on the main diagonal and zeros on the off diagonal. And what is interesting is that so the question they ask in the paper is how much better this Q move would actually establish Nash equilibrium in the game, which would allow you to avoid this dilemma. And they found out that for gamma, which is P over 2, a new Nash equilibrium emerged, which is actually QQ. And this result has been further developed by these 2 papers by Dooley, Xu, Shi, Wu, and the others. And sorry, I'm probably terribly mispronouncing the names. But they find basically that, and not find, but they actually experimentally measure it on the quantum computer. In this, this is a report in the first paper, when depending on the gamma, which I said is the measure of the entanglement between the 2 players. So how much do we entangle them before they manipulate and they play their strategies? You have this classical region up to a certain level of gamma, where the mutual defection is only Nash equilibrium, and above certain under gamma up to pi over half, you have this quantum region where QQ is new equilibrium. And in between, you have some like phase change between them, where QD and DQ are Nash equilibrium. So yeah, the combination of Q and the fictional strategy of one of the players. So if you, and this was the result I believe Alex Wendt was referring to when he said that with higher entanglement, you actually see more cooperation. So this idea of this paper is that if you increase the entanglement you get from this classical region where mutual defection dominates to this quantum region, which is not, which is where the payoffs is the same as if you apply mutual cooperation in the classical game. So it seems that you actually go to the region where cooperation is the stable solution of the game. Okay, and that's I just will, sorry for being 7 minutes longer than I expected, but I would like to just conclude to what I said. So it seems that game theory goes well with quantum algebra. I think, I hope I convinced you that it's kind of intuitive what we can do there. The papers that have been published show that classical games can be generalized into the quantum domain by allowing either superposition of states or strategies or entanglement of the players. And the crucial question, at least according to me, is how much does it correspond to the classical games? So whether we are actually solving the same game or we are introducing new category of games or class of games. There are not many experimental results, so lots of space for PhD projects or whatever if you want, and possible. And this is the point I made in the first slide, which I say is the promise of quantum game theory, is the possible way how to scale up the ideas that we have in cognitive science to the social level, because we talk about 2 players, but we can have games of n players or infinite number of players, and it somehow speaks of the possibility of the social phenomena. Okay, that's all. And I will just show the references, and I will address the questions that I had there, or any other questions that you may have.
Thanks a lot, Jakub. Let's see.
I will start with header question, if I may. Jakub, is there practical application for these strategies for real-world problems, incomplete data, or potential for more efficiently synthesizing ensemble data models? Practical application, yeah, I can point out to the work of my co-worker Catarina Moreira. She actually used these models in different versions in her PhD and in later work. Especially for the problems of, for example, missing data in the data set. So actually how to, I'm not that familiar with those algorithms. She's a computer scientist, but there is I would say a practical application of the use of these models as well.
Do you think you could post a link? However, in the chat, we can't copy and paste from there, but if you could put it in the Q&A, we can get to the Q&A.
Yeah, I can write the name, and she has like tens. Yeah, I would say.
Her faculty is what school?
She changed the school recently, I believe last week, and now is in the Technical Institute in Sydney, if I'm not mistaken. If I'm not Yeah, but if you look at her work or her PhD, for example, this like use of quantum modeling to deal with the incomplete data sets, it's amazing.
Okay, thank you. I mean, I'll follow up with you anyway, but I so appreciate that. Thank you.
Yeah, welcome. And yeah, I saw Eva, hands up.
It was just a quick question. I can find your papers. Did you have a book as well?
Not yet, okay. But I would say in the making, but like I would say in 2 years.
I found your papers. I think that you have a lot of information that would be helpful for my work.
Yeah. I can, yeah. The idea of this like categorization of games, we will present in the conference in September. So we'll have draft paper there, and hopefully by the end of the year, this could be somehow sent to the reviews. So hopefully it will be accessible soon.
Thank you.
Yes, Matt.
Yes. So I wonder, you made a different distinction between the one shot and the repeated playing of the game with some sort of memory. So whether the memory was maybe Markov, like the last play only, or whether the memory was the last 5 plays or whatever. Anyway, in the big scheme, does the analysis of the quantized version lend itself to knowing kind of the difference between the one shot and the with memory repeated? Is there any new results along those lines to compare those?
It's a great question. You know, this Axelrod result is used, as you definitely know, for explaining the evolution of cooperation. Yeah, so if this like mutual interaction, long-term interaction with the others, ask you to be more cooperative because you expect to be interacting with the same person the next day, or if you're in international relations, you can defect. Czech Republic can defect Poland today, but we need to deal with Poland tomorrow. So it's probably good reason to be more like trying to build some trust in between. So that is the general idea of how repeating the games can change the structure. So this is the basically this argument is that people cooperate in those one-shot games because they are like socially learned or primed to do so by their long-term interaction, their normal social life. But the question was whether quantum model change it. I don't think it relates to this argument, but I think the main promise with respect to this is this idea of entanglement. Yeah, so I think what is intuitive is that this assumption of classical game theory that the players are totally independent if they are in long-term relationship, if they like interact regularly, that we can think of them as like completely separate units, which does not create this mutual space. So I think this is the promising area where quantum model can think about introducing more coordinated actions. But I just want to say I do not agree with Alex about that in introducing entanglement only increase the cooperation, because in battles of sexes, if you have this maximal entangled state where they always end up in different places, then okay, entanglement does not mean anything. It's just like reinforce the non-cooperation. Yeah, so more entanglement does not always mean more cooperation in my view.
Well, you can have the maximally anti-correlated state.
Yeah, so. Yeah. That was like not the bus states I presented, but the other two where you will always end up in the other place. But I just want to say that there are games that you have K and L and X and Y strategies, that the games is not symmetric. So they basically speak about the same. So the question is what would be correlation and anti-correlation in that case? But the point is that it will not always lead to good results, I'm afraid, if you completely untangle, because it can be like in vicious cycles when they never agree with each other, and so if they end up in this like situation, then this situation does not lead to this anti-coordination, that does not lead to cooperation.
What is interesting also is looking at this entangled state in the Battle of the Sexes, I think, where you showed it. Like to think about mechanisms which can, like in the so-called real world, which can just create these entangled state. What does it? Because of course, in the math is simple, but how do you get to an entangled state in the real world? And one possible mechanism, I mean, I think about like this picture of people who know each other or are new to each other, so newly introduced. So I think it's helpful to think like when you are in a team, then possibly you will change the strategy, but in unison. And but what makes you change is not captured in the model, but it doesn't need. So it could be an external factor, which is unknown, but whatever it is, it will define a certain state. But yeah, this would be more like a hidden variable theory, like which would introduce this correlation. So probably we are back in the classical setting then.
That's exactly, I just wanted to ask if what does it mean if you in fact, first of all, is it possible? Sorry, my camera is making itself. Is it possible to include variables? Because variables seems to be relevant for the games. It's just a stupid thing, you know, the weather. You know, what is it possible to include variables? And if yes, what does that mean, and how does that change everything? And one very simple question, and I'm sorry because it could be very banal, but or naive, but I didn't really got the issue between what's the word, compatibility and incompatibility. Because to me, the first question, I'm coming from humanities. The first thing is who defines what is compatible or not. And if Linda is not compatible with bank teller, why not? I didn't get that really. And then what I didn't get
I should write it down.
Okay, thank you.
Go ahead. Go ahead.
What I didn't get as well, it also seemed to be so logical from your perspective, or simple, but the issue with Picard and Q. Picard has two possibilities, and both are the same. You know, both are, the coin is standing up. How does that come? And why is it so? And who says that? And I just can't logically grasp that, you know, and not even intuitively, you know, even if I go intuitively inside, I don't get it. Thank you. That would be great.
Thank you.
More about that.
Great question. I will try to address our 4 questions. So first, with respect to entanglement, that's the, I would say, key question you should ask when you are dealing with those models. Where does this entanglement come from? I believe that Alexis' answer is through language. Yeah, so that's the mean by which we somehow correlate non-locally the strategies. But I just wanted to play. I skipped the point on my slides, but what is quite interesting from my perspective is that we can think of two versions of entanglement. One is realism. So we are talking about entanglement of the players, but the second one is simpler, and this is cognitive entanglement. So if I create this mental space where the bases are the outcomes, I can see the game as, okay, we will always end up in the same game, same place, and it's not possible that we are anti-correlated. It can be like my perception of the game, and in that case, it's no like a real entanglement between Alice and Bob, but it's me, Alice, thinking about it, and if I see it as entangled, then I play the game differently than if I'm not. So that's like another level to this discussion, I would say. I don't know whether it's interesting, Michael, but that's I just rambled about this concept, which is quite, for me, interesting. And I will first address this compatibility questions or incompatibility. That was, I would say, the main topic addressed by Emmanuel Potos. And basically the idea is that, in physics, if you have incompatible variables, we cannot measure them at once. There is Heisenberg uncertainty that says, for example, between position and momentum of the particle, you cannot measure both with certainty. You measure once or measure two, or you can increase the precision of your measurement in one, but you will lose some precision in the other, and so on. And this is the idea of incompatibility of the questions. Yeah. So for example, with Bush and Gore, if those two are incompatible, then my answering in one of those two incompatible observables, I change my position in the other. So it's like this multiple projection to, yeah. So, and yeah, that's the big question I believe you asked, which questions are incompatible and which are compatible. Like what pairs of questions are compatible or what pairs are incompatible. My answer to this is, I would say it's an empirical question. So in physics, I believe we just like find it out in the experiments. We did not theorize it, at least that is my understanding of this. And I believe one of the hints is what, who was it? I don't know which of the speakers, but it's the familiarity of the issue. So if those two, basically, if you are not able to grasp both questions in one mental space, then they are incompatible. But if you have like this mutual mental space, which includes both of these questions, that they are compatible. And what is the most interesting for me from the perspective of social sciences, which I try to work on somehow, is this idea that first and third person perspective may be incompatible. So basically, me thinking about the others. And if someone is my wife, then it's not so much others as it is me. So I will probably create common mental space for her and me, but I may create different incompatible mental space for me and complete stranger or someone, you know, which I do not like or something like this. So that probably goes also to this entanglement question, I believe. And with respect to Picard, yes, the game is unfair. The Q is, you know, he can do everything if you know it from the series. And he is like, you know, he pops up off the space and to return to the ship and do whatever. So it's not symmetric. You know, Picard is limited to these classical games. And if Q introduce this superposed state where, yeah, basically with classical strategies, Picard cannot manipulate. Yeah, so it's invariant to what Picard can do, basically. Yeah, so it's not, yeah, it does not have physical interpretation. You cannot play the game, but yeah, it was great. It was one of the first papers, and I will invite you to see some episode with Q, and it will clarify probably. Yes, Zrinka, you are muted. Zrinka?
It's just it's fascinating to think about, you know, the possibilities like this. What I originally wanted to work on, like, would be so amazing, but it's like so far beyond what we can do right now. But like, what would it be like if we actually take groups of people and actually like watch, you know, like what do these two people do, like just on, let's say, political polarization issues. That say, you know, on Facebook or on social media, and they are interacting, and somebody might kind of maybe have an idea what their opinion is, and then but their friend says this, and to just watch like how they decide where they're going to be based upon what they think other people are, and then based upon if we throw like the whole concept of our senses, like what we know to be true, but like our friend is showing us something that may or may not be true, and like all of those decisions that roll into that. But you know, I think we're probably 5 to 10 years before we're even close to being able to look at that type of thing.
Yeah, but if I may react to it with 2 notes, in classical game theory, there is amazing job on group decision theory. So you do not have individual players playing the games, but groups. And they monitor the communication between them. And it's quite interesting, the results of this. For example, John Cagle from Ohio State University works in this area. And it's also like, it's quite interesting stuff what they do. And with respect to what you said, I think it goes back really well to social constructivism research in IR, this logic of appropriateness. And, you know, we do what we do because we think it's appropriate, but it's appropriate because our identity. So if we believe that we are of certain identity, we believe this is appropriate. But it's really depends on the peer pressure. So this, like, you know, including thinking about the others into thinking about myself is crucial for social phenomena. And so this is what quantum game theory try to model in the, like, you know, in like controlled environment where you have only 2 strategies and 2 players, but we can try to scale it up or to try to understand broader problems with it. I'm talking too much, sorry. Yes, Matt?
Oh, I first want to say I agree with, oh, where'd she go? The
Zrinka?
Ava,
Yes,
was it Ava that said, you know, it'd be interesting to get these groups together with the
Eva.
polarization, right?
Yeah.
That was Eva, yeah, because it was mentioned in the previous talk that you know, there's grant money to be had for this kind of stuff. The polarization, the American polarization in the political scene. Anyway, my question to you is hopefully quick. Let's see. So is there one notion of quantum game, and this is one of the leading ones that you purport is the leading concept, and there are other competing versions of quantum game, or is it more or less a consensus by now? What's your thought?
Oh, yeah, good question. As I said, the problem is that the literature is not, or the field is not really vivid, I would say. So there was lots of papers, but they are quite dated now. And when I've read about like 100 papers that somehow address this issue of quantum game theory, but there was no universal frame that was used in those papers. And what I presented today, and this is the result of like my work in May or June, is that I seem to start seeing some pattern there in this like mess. So I think we can, with this like, you know, this like either thinking about strategies or combination of strategies, we can actually include like 90% of what has been written in this like general framework. So this is why I think it's useful. And whether it's the only one, I doubt so, because, you know, we are still limited to, I would say, only a bunch of the concepts that are available in quantum theory. For example, there is no dynamics in here. So, you know, you may also start to think, for example, if you are thinking about repeated games or long-term games, whether there will be some effect of the fact that you will let the system evolve if, you know, if you have, but that would include this like thinking about Hamiltonian, and I don't know, which I don't know how it would look like in this context. So I would say it's not definitely all, but there are definitely avenues
I
how
think
to explore it further.
Yeah, in order to talk about equilibrium in any kind of sense, you kind of conjure the notion of evolution or dynamics already, because equilibrium means stable in the long run, right?
Yeah, but you know, in a Nash equilibrium, suppose that this is stable, that this is okay, the game will gravitate toward this, and if you somehow teach the players to do so, they will like gravitate toward this. And that's quite like counterintuitive from the perspective of quantum theory, where you have this like you know this vibration which is always there, even in the like ground states and everywhere. So and by the way, I think one of the Alex asked about it, what are the like big questions that should be addressed in different fields? That's one, obviously one of the questions. What is Nash equilibrium in quantum game? And in four-dimensional problem, if we have factorialize initial vector, that's we still have Nash equilibrium. So this like transition to classical games is there, but the question is, what does it mean for the other possibilities? But I would say Nash equilibrium does not exist in all quantum games. Okay, Marcin, and I'm sorry, we used all of the time, and I'm happy to address whatever questions, but I don't want to keep you here, so feel free to turn to bed if you are in the time zone that ask you for this.
So it's quite late now. Okay, so I've got a tricky question. I think if there are or is there a kind of generalization of this quantum games? I mean, in the sense of quantumization of quantumized games, that is introducing some kind of meta quantumization. So you mentioned, and probably you answered partially to this question, because you said that the genders differ in the different strategies. That women have different strategies when gaming than males. So I would say that. So the gender differences for me personally are not so much interesting as, for example, differences among members of different social classes. Mm-hmm. Because if it would be possible to generalize it in some way, I mean the games, by repeating them, you know, but then even if you repeat these games, then you still need to have some kind of generalization of the results, yes, and that would be especially interesting in a case of comparing the different strategies among members of different social groups, because this would lead or take us a little bit closer to the fundamental question on the ground of sociology about keeping or generating social order. So in fact, I have two questions. So the first one is about generalization, and if there is a quantumization of quantumized games. So this is more technical, I would say, because I'm interested in such meta level of this games. And the second one, which is more practical, is it if such a strategy of quantumization or having the results not at the level when the game is conducted one by one, because yeah, it's a different story, but at the group level. So yeah, okay, thank you.
Yeah. Okay, I will try to be brief. With respect to this generalization, I have 2 points. First of all, in my experiment, we checked for classical social demographic, variables like education, age, size of the city, income, and so on. And the only difference we found was gender. So I'm not saying that that it's only one that you may find there, but in my experiment this was the case. But this is the second note for the first question. With respect to other experiments that has been done in game theory or in decision theory, the effects are surprisingly analogical across different contexts. So, for example, surprising level of altruism in dictator game is quite same if you do it in well-educated society in a city, or they've done the same experiments with members of Amazonian tribes, and you find similar patterns there, which is it's probably say something about humanity then. But I would say, I think actually this kind of research can provide some answer with respect to what Alex was presented on Wednesday, whether this has been educated. Yeah, so whether we have been, educate. It's possible that we've been educated to think of the world in this incompatibility, that in this individuality without entanglement and so on. And it may be that, if you do this experiment with the university students of economics, you would have different results from students from critical security studies, or I don't know. Yeah, but that's definitely what it's been done, but definitely not in quantum context, because as I said, we have only few experimental results there. And with respect to the second question, which I'm not sure I fully grasped, but yeah, I think you were asking about like broader social theory, how it can be used to explain like patterns in society. I just want to say that, it seems simple, but it's still the step from cognitive models to the situation where you have 2 people, but you can have games with 10 people, and I've run this experiments with 20 people. Yeah, so it's like first step for scaling up for the society. So
that's what I wanted to know, because okay, yeah, that's interesting. Thank you.
You're welcome.
Good stuff, Jakub.
Thank you, Matt. Thank you all for staying here so late.
Thank you very much. It was so interesting. Thank you.
You're welcome. So, Michael, some concluding words for Bootcamp, or?
Concluding words. Let's see. Well, I hope that so I'm looking forward to your comments in the survey, and maybe there's a way for those who were part of this bootcamp to join one of the reading groups which we have, and to engage on Google groups. And otherwise, this was a great workshop, and I just had hoped that there would have been somehow more advertisement, or so it had reached more, because my impression is many people don't know about this workshop, and who would otherwise be interested. So if there are any ideas how to increase the reach for next time, would be great. And yeah, videos will be uploaded by the end of next week, I guess. And yeah, I will send the information to the reading groups, and so I will we will send out this survey questionnaire on Monday probably, and then there will be a checkbox. Are you interested in joining the reading group? Are you interested in joining the Google group? And so yeah. And yeah, thanks for staying so late, and thanks, Jakub, for running this tutorial on quantum games. This was really cool.
Yes.
This time we had enough time to cover everything. Last year we had to skip a part.
That's right. Well, I see Kelly is also here. My question probably would just be logistical. When will everything be posted to the website so that folks who missed, we had a lot of registrants for the workshop, for the, maybe not this workshop, but the whole conference, right? And they were counting on not only the recordings, but also the presentations to be there. So are you confident that the presentations and slides and recordings will all be there, like say Monday, Tuesday?
No, it's not so easy, because Kelly unfortunately is not really like, she was the coordinator as we were running the bootcamp, but all the work on the web page, and so this is Kelly doesn't have access anymore. So we depend on 2 other people, and so my guess is sometime by next week. So by the end of the week, we should be all good. Also this time, the videos will be edited, and they will be uploaded. So there's now a YouTube channel. This is very nice, but this requires some work. And for the slides and so we will have to wait for the speakers to send them in. So by the end of next week, if everything goes well, something like this.
Oh yeah, the YouTube is a good idea because that's more exposure. Thank you.
Okay. Thanks for staying so late, and thanks, Jakub, again.
Thank you so much. Thank you.
It was a pleasure. Thank you very much.
Bye-bye, everyone.
See you somewhere else.
Next year.
Yeah.